And hello YouTube, welcome back. So today we're going to talk more about some of the extra functions you can use to assess the stabilities of your transfer function. Okay, so this is somewhat of the end result we are going to get, where you can perform step tests and you plot Bode plots. There's even a way to define a transfer function via Pos and Zeros, but it's not really recommended because I'll show you later. Okay. So how do we get some of this stuff working? So I'll just walk you through some of the features here. I'm going to start from where we left off the last video. So this is just a preview of what we might be doing. Okay, so I'll close this and let's take a look at this VI here. Okay, this VI, when you press run, we can actually go to various transfer functions. The first order with delay, second order, third order, and even some custom transfer functions here, which you can just change the coefficients like in real time. Okay, so I'm going to stop this, and let's say I want to get the Pos and Zeros of this transfer function. How do I do it? Okay, so it's a bit quite simple. Press Ctrl E. Okay, and all right. Just to make the computer like use less what do you call that, CPU power or CPU processing speed, I'm going to lengthen this wait time. Okay, and well, before we had this transfer function equation, okay, which we can just pull to the right here. Okay, so if you want to start analyzing, let's say, the Pos and Zeros of the transfer function to see whether the thing is stable. Okay, is the input to output response stable? Okay, it's very simple. You can go to Control and Simulation, and you go under Control Design. Okay, go to Model Construction, and you can see CD draw Pos zero gain. Okay, let's go through it again. So normally, remember we have this thing called draw transfer function, right? So we can go to this place, Control and Simulation, Control Design, Model Construction. So beside the draw transfer function equation.vi, there's a draw Pos zero gain equation.vi here. So we can just take that and put it here. And very simple. We can wire this up to this pinkish thick wire, and we'll give it an indicator where the output is equation. Okay, the output is equation. So let's create indicator. Then you can just put Pos and Zeros. Pos and Zeros. Okay, so the Pos and Zeros equation will be here. So I can just make the box a little bit bigger, or yeah, roughly match, and I'll just press play. Okay, now look at this. It will give you the Pos and Zeros. So if you have a transfer function on the left here, and you kind of display in a neat polynomial kind of method, kind of stance, you can actually decompose all of this into the various Pos and Zeros very easily. Now, for example, you can see the gain here is 0.833333. You have a 0 at s plus 2. Okay, you have a pole at s plus 0.734. So s equals minus 0.734. This is a real pole. Then you have a complex pole here, s squared plus something almost 0.6s plus 0.226851. Okay, so the thing is this, we don't know whether this is actually stable yet. We know that there's one pole at s minus 0.734. Okay, if you look at the denominator, they're all nicely factorized for us, but here it is not exactly in a way we can see just by inspection that it is stable. So I'm going to stop this, and well, what can we do to make it easier for ourselves to see whether something is stable? Okay, you can go to this Pos and Zero VI. Go to the top, there'll be one of these wires that is called display format. Okay, go to one of these wires called display format. Okay, this inputs, right click, and you put down there create control. So this will be the display format. You can do Pos and zeros display. Okay, sometimes I spell zeros with an E. It just makes me feel a bit more comfortable. But if you disagree the spelling, just write in the comments, let me know. But yeah. Okay. So what is this Pos and zeros display? Okay. This will actually enable you to control what the output looks like partially. So if you press play, and we by default it is set at standard. Okay, the display is set at standard. You can change it to engineering. Okay, why is engineering good? Because now you can see the real and imaginary parts. Okay, so now you can see the real and imaginary parts. Excuse me. Yeah, of your poles. So for example here, S plus 0.299318. So this is a complex pole. You have a plus minus 0.730486i. So that's a real part, that's an imaginary part. Imaginary part will be, of course, dealing with sines and cosines. The real part deals with exponentials. So you want the real part to always be less than 0 as far as possible. Okay, you want all your poles to be less than 0 in order for it to be a stable system. Okay, at least in theory, a stable system should have all poles at the left hand side below 0. The real parts of the poles are all below 0. Okay, so okay, let's do GIMP. Yeah, so just some revision. You have the imaginary part, you have the real part, and this is 0. All your poles should be over here and on the left hand side. Okay, so S equals to sigma plus j omega or I omega, depending on which one you which course you take. And this is just an imaginary number. Okay, so for stable poles, they should all be on the left hand side. That means this real part of S should be less than 0 or less than equal, less than equal to 0. Though less than 0 will be the better one, of course, because that indicates exponential decay. Okay, because E minus sigma will be inside your time domain transfer function, so to speak. All right, so this will be representative of here. So all your real parts of the poles should be less than 0. And the long story short is that, okay, if you take a look at this engineering display, S plus something something, this indicates pole on the left hand side below 0. This one also indicates the real part of the pole is also on the left hand side. So by this you can see that this transfer function is more or less stable. But if I just randomly add numbers and everything, you'll see, okay, this is still stable. Okay, this is still not so stable already. You see there's a S minus 0.2824. Okay, so what does that say? That says that there is a, let me stop this thing and stretch the equation a little bit more. Alright. Okay, so what does it say? This says here that there's a pole on the right hand side. Once a pole is on the right hand side, then definitely you're going to have issues. You're going to have instability issues, because some of these frequencies will result in exponential growth. Okay, so I'm going to stop this. How can we see it even clearer? We can do it. You can do this step response. Okay, if you want to analyze some stability of this transfer function, okay, go to control and simulation, control design, go to this part saying time response. Okay, one more time. Right click, go to control and simulation, control design, time response. Okay, time response, you can take a look at one thing called a step response VI. Click that. Okay, and you place it here. Okay. So there are lots of inputs and outputs here. So let's look for one saying the state space model or transfer function model. So you can select automatic. Okay, that will detect the kind of transfer function model you are having, whether it's a state space in a state space form or transfer function form. That's okay. This using an automatic mode will enable you to just put in any of those. So of course by default it's in SS or state space, but once you draw the wire over to the state space model, it automatically becomes a transfer function model. Okay, cool. And how do we see the results of this step test? Well, you can take a look at this thing. There'll be an output called step response graph on the top right. Right click and click indicator. Then you'll see this step response graph. No problem here. So step response graph. Okay, let me save. And let's put the graph at a nice place. Okay. Okay, so we have a step response graph. And let's press play and see what happens. Okay. So apparently this step response graph, as you have a step response, it will go all the way up to 14 and then it will go down. Why is this so? Because if you take a look at the pole or zero here, you look at the pole here, it's s minus 0.282 plus minus 1 something something I. So this is a increasingly exponential response, but it's a sine wave, kind of a sine wave exponential response. So let's take a look, see what can we do to do this. So we can go and adjust the time range, because this thing only goes from 0 to 9 seconds, which is not very telling. But if you right click the time range, you go to control, you right click again the step response. You can change the time range for step response. Okay, step response. Okay, you just go to the node or button that the input saying time range. You right click that node and just create control. Okay, then there will be a controller there. Press Ctrl E to get back to the diagram. Okay. Okay, so by default, all of these values are at -1. Okay, all of these values are at -1, meaning to say it's automatically determined for you. But let's say you don't want -1, right? You want to adjust the values. So T0 is of course your start time, TF will be your final time. Let's give it 100 seconds for example. Okay, so it should ideally go from 0 to 100 seconds in automatically, and the change in time. Alright, let's see how much time I have remaining. Yeah, the change in time, dt, is -1, or otherwise it's automatically determined. So we press play. Now we can see that this is a exponentially growing graph. Actually, you don't even need 100 seconds. Maybe 50 seconds will do. And you can see it goes up to 200,000. Let's put 10 seconds. Okay, so it goes up to 14, it goes back down to 0, then it goes back up again. So maybe we can, if you take a look at the 20-second mark, or 15 seconds even, we should be able to see the thing actually spiraling out of control. So this is an unstable step response graph. Of course, you know it because there's a pole that's causing everything to be unstable. So let's put this back to 0, and now we can see okay, we can see that alright, this graph is pretty stable. If you put 100 seconds, okay, so you put 100 seconds, then your step response, it will just be like constant after a while. Okay, if you want to shift it back to automatic, the final time, just put -1. You should be able to see everything. So you can play around with it and see whether it's stable or not. Of course, the most important one that tells you whether it's stable or not are the poles. So make sure to look at this poles and zeros indicator to see whether your transfer function is stable or not. And your step response graph will then be how do you say? Your step response graph will just be confirmation of that. Okay, let's say you want to do some frequency response. Okay, let's say you want to do some Bode plots here. So where do you find that? Okay, it's pretty simple. Go to the same place, control and simulation, control design, model construction. Then, you should go to frequency response. Okay, one of them will be CD Bode VI. Okay, again, right click, control and simulation, control design, frequency response. Go to the Bode VIs. Alright, so again, all of your stuff, there'll be lots of inputs and outputs. Go and look for the thing saying state space model or transfer function model, because again, this thing is automatic. As long as you wire in a transfer function model of any kind, it will just automatically adjust this Bode plot VI to display that, oh, okay, we are dealing with a transfer function now, not a state space model. Okay, so the outputs, there will be Bode magnitude and Bode phase towards the top right hand side. So at the Bode magnitude, just click indicator, then you have a Bode magnitude, Bode phase, create indicator, then you have a Bode phase plot. So these plots will be done for you very nicely. So they will just appear at random spots over here, so just drag them down to somewhere where it's like palatable for you. So okay, so we can press play again. It should give you the Bode phase and magnitude plots. So the phase plots and magnitude plots are as follows. Okay, of course you cannot see from this Bode magnitude plots that it is a very what do you call that? You can't quite see that it's an unstable system from these Bode magnitude plots. Okay, I mean ideally there should be if there's a pole, a pure real pole with that's on the right hand side, you will be able to see if you increase the frequency to a certain range, you should be able to get this infinitely going up. I mean, you should be able to see the pole there. Unfortunately, we don't have pure real poles here, so you can't really just do something like that. Okay, so you won't be able to see the you won't be able to see this what do you call that? You won't be able to see the pole, so to speak, in the Bode magnitude plots. Okay, you won't be able to see it, but at least from the transfer function, you should be able to take note that, okay, this thing is unstable. Okay, it's an unstable system. Okay, so let's make it stable again and see what happens. And you see the Bode plots are still pretty much the same. Okay, we put a number 6 there. Yeah, so there is some gain at the beginning, but it just goes down as the frequency goes up. Okay, so these are the Bode phase and magnitude plots. Mostly from, you can actually read this plot somehow by noticing the slope downwards, and you can see there's a turning around point at about 1 Hertz. Okay, the frequency is about 1. Okay, not exactly 1 per se, but very, very close to 1. It's a bit hard to zoom in, but yeah, the place where it starts to drop down is over here. And if you look in the pole plot, in the poles, okay, if you look at the poles, there are actually 2 places where yeah, okay, let's put some context first. If you have a pole if you have the pole at a certain frequency, tendency is for the Bode plot to start sloping downwards at 20 dB per decade. That I assume you should know. Okay, if you have a pole at a rail part, it should slope downwards at 20 decibels per decade. If you have a zero, it should slope upwards at 20 decibels per decade. Okay, so do we see that happening here? A bit hard to see. Yeah, it's very hard to see, but we do see the downward slope at around 1. So it's on the order of magnitude of 1 that this Bode magnitude plot actually starts to slope down. So this tends to be okay, not too bad. Seems legit, at least. Let's try the first order with delay. We can see the step response is very straightforward. Okay, the gain is at 2.5. The S is at 0.25. So at 0.25 we should expect a sloping down. Okay, 0.25 here, we should expect a slope down in the Bode magnitude plots. Bode phase plots, yeah, that's what happens as well. We see a sharp sloping down from 1 Hz onwards. Now this is the most easy kind of transfer function. So the nice thing about having this case structure is that you can just keep switching around your Bode magnitude and Bode. You can switch around the transfer functions and you can instantly see these responses. Okay, there's a frequency and time response. So third order will be like so. And of course, if you're wondering whether we can change the magnitude of the step response, okay, instead of making it automatic, let me stop this first. Let's check whether this is available. Yeah, you should be able to change some of the initial conditions, and you can create control for that. Yeah, you can create control for these initial conditions. Okay, the wires are getting messy. Yeah, you can create stuff for the initial conditions, and you can even get step response data coming out. So let's see what the initial conditions look like. Okay, they give you some sort of a matrix here to play with. Okay, let's move the stop button here. Okay, so we can play around with the initial conditions. So 1. Okay, so you can start with the initial condition of 1 or 2. It really is up to you. Okay. Okay, they'll give you an error. Okay, so you can only play with the the 0 columns. Okay, so the stuff at the 0. Okay, let's play again. 0. You can switch it to 1. Continue. Stop. Okay. Okay, so I mean, looks like this is not the way to do it. Yeah. Anyway, yeah, looks like it's a little bit not that straightforward to change the magnitude unless you know what you're doing. Okay, let's see whether there's anything else we can do. Step response out, error in, blah blah blah. Okay, I think we shall just leave it as that. At least this VI seems more intuitive for this. Of course, if you know how to change the magnitude of the step response, do let me know. But at least for this VI, doesn't seem like it's that intuitive to change. Okay, but okay, at least this does show you the proper step responses which you can obtain. Okay, step and frequency response. Not too much of a difficulty to do those things. Pretty straightforward. So yeah, one last thing. Okay, let's see whether I have enough time. I'm about at 24 minutes, so I think I'll stop this video for now. I hope this shows you, It's quite easy to get time response and frequency response if you have a given transfer function. You want to do it in Labview, no problem. Okay, thanks for watching. Bye bye.